If I had to guess, the reason that chair flips feel impossible is that you're probably considering the chair structure as a flat drawing instead of a three-dimensional representation. In this video, we're going to replace all those confusing chair rules with one simple visual, a globe. Hey there, ninjas. If chair structures have always felt like something you were supposed to memorize, you're not alone. Students file away a collection of rules. Axial bonds point up and down, equatorial bonds point sideways, chair flips turn axial into equatorial, and eventually it all starts to feel like a collection of magic tricks. But the real problem is that most students don't develop the correct three-dimensional model of the chair structure. Today, I want to replace all of those disconnected rules with a single mental model. Treat the chair like a globe. If we're looking at a globe of the Earth, we have a North Pole and a South Pole and an equator. If we wanted to, we could tip the globe and look at it from the North Pole. Now the equator would be around the ring of the circle, and we'd really only be able to see the northern hemisphere. Now imagine we had a translucent globe, and we placed 6 carbons around the equator of that globe. That's our starting point. The ring carbons live around the equator of our globe. Once you picture that, a lot of organic chemistry becomes a lot easier, because now the question is no longer, which rule do I apply? Now the question becomes, which direction is this bond pointing relative to the globe? Let's start with our normal cyclohexane hexagon, the one you've been drawing for a while now. When you draw this structure, think of those 6 carbons of the ring as around the equator of our globe. If I were to take this globe with our 6 carbon atoms and tilt it so we're looking at it from the North Pole, I would be able to see those 6 carbons of the hexagon perfectly placed around the equator. And that's what gives me my cyclohexane hexagon. Now let's add wedges and dashes. Recall that a wedged bond points towards your eye, and in our globe model, that means the wedged bonds point up towards the North Pole in the northern hemisphere. And recall that a dashed bond points away from you into the plane of the page, meaning that all 6 of the dashed bonds point away from the equator down into the southern hemisphere. So when you draw the flat hexagon and wedge means up and dash means down, up and down are not arbitrary anymore. They refer to which hemisphere the substituent occupies, either the northern hemisphere for wedges or the southern hemisphere for dashes. And that idea becomes incredibly important when we switch over to chair structures. Now, let's rotate the globe back to its normal perspective. Here, we're kind of looking side-on at the globe, looking at the equator. In the translucent globe, we can see all 6 carbons, even the ones in the back. And when we imagine looking at the globe from the side, that's exactly what the chair conformation is. We're looking at the same 6 carbons, but now we're viewing that globe side-on. And here's the most important observation. Notice that our side-on perspective isn't truly side-on. We're biased a little bit towards looking at it from the northern hemisphere. Our eye is actually a little bit above the equator when we look at the globe. Because of that perspective, the 3 carbons on the bottom are closer to you than those 3 carbons that are nominally higher up on the screen. Let me say that again to make sure that we're clear. The top carbons in a cyclohexane chair are not higher because they're physically above the bottom carbons. They're drawn there because they're further away, and we're looking at it slightly north of the equator. The top half represents the back of our transparent globe, and the bottom half represents the front side. And once you understand that, chair structures stop looking flat, and you can finally start to see its depth. Now, let's discuss axial and equatorial. There is an imaginary line that goes straight from the North Pole through the center of the globe and down to the South Pole, and that would be the vertical axis of our globe. All of the axial bonds around our cyclohexane chair are parallel to that vertical axis. That's why they're called axial. Now, notice something. Some chair carbons point up, and some chair carbons point down. If a chair carbon points up, its axial bond is up into the northern hemisphere. And if a chair carbon points down, its axial bond would point down toward the southern hemisphere. So you don't have to memorize an alternating pattern. You can simply look at the carbon. Up axial. Down carbon, down axial. The globe geometry tells you everything. And as for the equatorial bonds, these bonds don't run parallel to the vertical axis of the poles. Instead, they point outward around the equator. That's why we call them equatorial. Now, because of carbon's tetrahedral geometry, the equatorial bond can't point perfectly perpendicular to the equator of the globe. It tilts slightly up or down into the northern hemisphere. In fact, it points slightly into the opposite hemisphere of that carbon's axial bond. So on an up carbon, the axial bond points up into the northern hemisphere, and the equatorial bond points slightly down into the southern hemisphere. And on a down carbon, the axial bond points down into the southern hemisphere, and the equatorial bond slightly up into the northern hemisphere. The direction is not random. It follows directly from the shape of the tetrahedral carbon. Now, let's talk about chair flips. Here's the mistake that many students make. They sometimes think we're physically flipping the chair over, taking the south pole and moving it up to where the north pole usually sits. That's not what's happening. Sometimes we take the globe analogy a little bit too far and think that the carbon atoms are circling around the equator, and that's how the groups move from chair flip to chair flip. That makes some sense and would actually fit the metaphor quite nicely, but that's also not what has happened. The carbons stay where they are around the globe. The globe is not rotating. The carbon furthest to the left stays the carbon furthest to the left, and the carbon furthest to the right stays the carbon furthest to the right. What changes is the direction the bonds point. All the carbons that were down carbons now become up carbons, and all the carbons that were up carbons now become down carbons. And when you rotate a down carbon to become an up carbon, its equatorial bond rotates up to being an axial bond, and its axial bond rotates up to being an equatorial bond. Same thing with the up carbons that become down carbons. The up axial group rotates down to be an up equatorial group, and the down equatorial group rotates down to be a down axial group. And now we can explain one of the most important rules of drawing chair flips. While every axial group changes to an equatorial group in the chair flip, a chair flip does not change which groups are northern hemisphere groups and which groups are southern hemisphere groups. Why not? Because a substituent never leaves its hemisphere. A group in the northern hemisphere stays in the northern hemisphere. A group in the southern hemisphere stays in the southern hemisphere. An up methyl group remains an up methyl group. A down hydroxyl group remains a down hydroxyl group. The only thing that changes is whether it's an axial or an equatorial group. So the next time you're looking at a chair conformation, stop seeing it as a collection of zigzag lines. See the globe. See the 6 carbons around the equator. See the axial bonds parallel to the poles, and the equatorial bonds pointing out away from the equator. And when the chair flips, the globe stays put, the bonds simply change roles. Once you can see that globe in your head, most of the rules you used to memorize become consequences of the geometry. And that's when chair structures finally start making sense. If your goal is to get better at chair flips, don't spend more time memorizing patterns. Spend more time improving the mental picture in your head and getting it down on paper. If you're looking for a companion skill, the perfect follow-up video would be how to draw the perfect chair structures. And I'll have that video linked in the description below. Keep up the great work, ninjas.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.